All right, so in this chapter, we're going to continue to look at the structures of different molecules. Um, but we're going to go a little bit further with it because with the Lewis structures we were looking at in the previous chapter, what these showed us was the arrangement of atoms in relation to one another, meaning what's bonded to what, as well as how the electrons are distributed. So where we have single versus in some cases double or triple bonds, where do we have lone pairs to fill in the valence shell. In some cases, we have lone pairs to exceed the octet on the central atom. But what we're going to start to look at now is the true three-dimensional shape of these molecules. And that's going to give us a better understanding of certain properties, such as like the reactivity and things like the polarity of these structures. And like I was saying, with the Lewis structure, they do a good job of, if we go back for a second, the arrangement of atoms, what's bonded to what, where the electrons are distributed, but it doesn't give us a true representation of what this molecule would look like. Because if we look at something like carbon tetrachloride here, looks like it's going to be a T shape, but that's not actually going to be the case. What we're going to see is something similar to what we have here, what we're going to be referring to as a tetrahedral structure. And what this is actually going to allow the electrons in the bonds, the electrons in the lone pairs to do is essentially just spread out as much as possible. And we'll see with a bunch of different examples how the Lewis structure isn't going to fully represent the true structure here. So if we look at just a couple generic examples, we've got AB2 and AB3. So what this is referring to is just A is the central atom, B in each case is going to be the terminal atom. And we'll see, even though in the top two, carbon dioxide and sulfur dioxide, we've got the central atom and then just two oxygens. So if we drew the Lewis structure, they may wind up looking pretty similar just because we're going to have one central atom, two terminal. But what we're going to actually be able to start to see with the three-dimensional shape is that because sulfur here is going to have lone pairs that the carbon won't, because these are going to be double bonds, what we're going to see is that the lone pairs is going to actually force these bonds to get pushed down. So instead of the linear structure, we'll see bent for something like SO2, even H2O is going to wind up looking similar to this, where it's not just going to be a linear structure. We're going to have the oxygen in the middle, and then the hydrogens both getting pushed down. And then with the next one, AB3 again, B just going to be whatever that terminal atom is. So oxygen or fluorine with the second two. Even though we've got the same number of atoms, what we're going to see because of the way the electrons are actually distributed in these is that we're going to wind up with three different shapes, three different structures for these ones. So in the case of SO3, we're going to see that there's going to be no lone pairs on this sulfur. So all these bonds are going to have to do is spread out from each other. They're going to be able to do that in just basically making a triangle shape. Whereas with something like NF3, or if it was even ammonia, so if we replace these fluorines with hydrogens, NH3 ammonia, there's going to be a lone pair here on this central atom, which is then going to force these bonds down. And similar idea with the ClF3. There's going to be two sets of lone pairs on this chlorine, and that's why we're going to wind up with an even different shape here. So the Lewis structure just isn't going to be able to fully represent the differences with these structures. And then with it, these are just going to be the basic electron geometries. So in each case, the red atom is referring to the central atom. The gray is going to be the terminal atom on the outside. And I said atom. In some cases, we're not going to have an actual atom here. We're going to have just a lone pair. So we're going to see a similar sort of shape, but the lone pair is just going to be slightly different. We'll cover that as we start to go through it. But with them quick, just so we can kind of see. Linear, of course, just because it's going to be a straight line. Trigonal planar. So because it's planar, it's telling us all three of these atoms on the outside are in the same plane. So if we had this molecule, we could lay it flat on the desk, and all three of these atoms on the outside, as well as the central atom, would lay flat on that desk. Whereas with the tetrahedral, what we're going to have is a triangle on the bottom, but then the central atom is going to be raised up a little bit, and then we'll have a fourth atom just coming off the top there, kind of giving us a little bit of a pyramid type of shape. And then now when we've got 5, we're going to have a triangle in the middle. So we'll see that these are called the equatorial atoms. And then we'll have the two atoms kind of going to the north and south pole, if you want to think about it like that. And then if we just connect all of these, we'll have a pyramid on the top. So with these three serving as the base going up to the top, and then just the reverse on the bottom. So that's why we call it trigonal bipyramidal. Trigonal, because we've got the three in the middle, and then bipyramidal, just because we've got that pyramid shape going in both directions. And then with the octahedral, it's going to be similar, but in this case, we've actually got 4 atoms on the equator. And actually, in this case, all of these angles are going to be the same. They're all going to be 90 degrees, whereas these are 120 around the middle. But kind of the same idea where we've got 4 on the equator, 2 on the poles, giving us the octahedral shape here. But like I said, not all of the electrons are always going to be going to atoms. So what we'll see is sometimes if we do have just all atoms on the central atom, we're just going to wind up with whatever that shape is. But as we take the electrons on that central atom and replace a bonded atom with just a lone pair, we're going to see that the electrons are still going to be sort of taking up that space, because ultimately these are all going to spread out as much as possible to minimize the repulsion from all of the negative electrons. If we have a lone pair here, it's still going to sort of affect that shape in terms of how these have to get spread out, but it's not actually going to sort of be seen in that case because we don't have actually anything bonded here. So it's still going to force those electrons in the bonds down, but it's not actually going to take up any space really. And then the same thing still. In this case, we're just going to have 2 of those bonded atoms get replaced with lone pairs. So you can see we would have a lone pair going up to the top here, a lone pair going to this corner, and that's why something like water is going to be bent. So we'll have the oxygen in the center, hydrogen bonded to it, but then we'll also have the 2 lone pairs, and that's why it's going to be a bent shape rather than just a linear one. Okay. And we've sort of referred to it a little bit, but with these molecules, what's ultimately going to be determining the shape is the electron pairs. That's why we'll see in a little bit that this is going to be called valence shell electron pair repulsion theory, VSEPR. But with it, we're thinking about electrons in the bonds as well as the lone pairs, because with all of those electrons, they're going to be negative, so there's going to be a repulsion between all of them. So it doesn't really matter if we're looking at the lone pairs or the bonded electrons. There's going to be that repulsion, and that's ultimately going to influence the shape, because the electrons are going to want to spread out as much as possible in order to minimize that repulsion. And when we're looking at those electrons, what we're going to be referring to them as is the electron domains or electron groups. So I'm more used to referring to them as electron groups, but the textbook I think uses electron domains, so we can use those interchangeably. But with these electron domains, what we're going to be looking at is typically just on the central atom, because that's ultimately going to be determining the true structure of this shape. In some cases, we may have multiple sort of central atoms if it's a larger structure. But the way the electron domains, or how many electron domains, I should say, are on that central atom are ultimately going to determine where those electron domains are sort of headed, and that's going to determine the structure. So when we're looking at an electron domain, what we're thinking about is a bonded atom or a lone pair. So if we look at A here, let me get the draw tool. If we look at central atom A, what we're going to see is we've got 1 lone pair. So that's going to be 1 electron domain. We've got 1 bonded atom, a second bonded atom, and then a third bonded atom. But since each of those bonded atoms, the electrons, even though we've got a double bond to one of them, are grouped together, they're still all going to count as just 1 electron domain each. So even if we've got a double or a triple bond, so with this top one here, for instance, even though we've got extra electrons here, we can still think about those electrons as being grouped together. So we would only have 4 electron domains on this, this example here. So again, when we're looking at the electron domains, each set of lone pairs counts as one, as well as each bonded atom. So in A, we've got 4 electron domains, just because we've got 3 bonded atoms and that one set of lone pair, or that one lone pair. And if we looked at any of the examples on B, the ones on the side would each have 4 electron domains because they've got 3 sets of lone pairs and a single bond. Whereas the top B here would have only 3 because it's got 2 sets of lone pairs and then just one bonded atom to it. But when we're thinking about the structures, we're going to be focused on the central atom because, again, that's going to be the one that kind of determines how the other atoms have to sort of spread out. Okay. And if we think about the electron domains just as balloons quick, what we're going to see is that if we have 2 balloons, so if we've got just 2 electron domains, the best way for them to spread out is just going to be 180 degrees in between them. So it's just going to wind up with a linear sort of structure there. And with it, you can kind of think about where they're tied as the central atom, and then each balloon as being an electron domain. So we could think of it as a lone pair, or we could think of it as a bonded atom. And now when we've got 3, what we're going to see is that the trigonal planar shape, because the best way for them to spread out is just going to be 120 degrees between each of them. But it's going to be so that all 3 of them are in the same plane. And that's why if we had these balloons, we'd be able to just lay them all flat on a desk or something like that, because they're going to be in that exact same plane. In this case, they're all in the plane of the screen. But if we just turned it 90 degrees, then we could lay them flat on a desk. But when we get to 4 electron domains, so again, think about where they're tied as the central atom. Now, when we've got 4 electron domains coming off that central atom, we can't have them all just in the same plane. So that's going to be why we start to see this tetrahedral structure, where we kind of wind up with sort of a triangle in the middle, but it gets pushed down a little bit because we've got this other electron domain at the top. So in this case, the central atom would be a little bit above these 3 that are making a triangle at the bottom. And then we've got the 4th one just coming straight off the top there. And then the concept that we're going to be focused on, or the term we use to sort of describe it, is VSEPR, VSEPR. And what that's referring to is valence shell electron pair repulsion theory. So if we just break that down, valence shell, just referring to the electrons in that outermost shell, because again, those are going to be the ones that are actually participating in bonding, the ones that are going to be involved in different reactions. So those are going to be the electrons that are actually kind of doing the interesting things in chemistry for the most part. And then electron pair, because when we look at these structures, we've always, or with the exception of radicals, but for the most part, we've got these electrons paired together either in bonds, where each dash represents the 2 electrons, or we've got them in the lone pairs, where again, they're going to be grouped together. And then the repulsion piece is just referring to the fact that these electrons are going to be negative. And anytime we've got like charges, they're going to repel. So what we're going to see with these valence electrons is that they're going to spread out as much as possible in order to reduce that repulsion. So that's going to be what we're referring to when we look at valence shell electron pair repulsion, VSEPR. And depending on the number of electron domains, that's going to determine the best way for those electrons to spread out. So again, when we're looking at the electron domains, we're thinking about bonded atoms. Doesn't matter if it's a single, a double, or a triple bond. Each bonded atom counts as 1 electron domain, as well as each set of lone pairs on that central atom. So depending on how many electron domains we have, we're going to have a different electron geometry. And what this electron geometry is showing us is the best way for those domains to actually spread out. But we will see there is going to be a difference in some cases between the electron geometry and what that molecule actually looks like if any of those electron domains are lone pairs. But if we're just looking at the electron geometry, if we've got, again, 2, 3, or 4, we've already seen those. So linear, trigonal planar, or tetrahedral here. But now when we add the 5th lone pair, trigonal bipyramidal. So the best way for them to spread out, triangle in the middle, 2 electron domains coming off the top. And then with 6, we're going to see the octahedral, where we've got sort of the square around the middle, and then the north and the south pole there, where everything's spread out by 90 degrees. But again, when we take any of these electron domains and have them be a lone pair instead of a bonded atom, we're going to see that it's still going to affect the geometry. So it's still going to affect the way they spread out. But when we actually kind of think about visualizing that molecule, we wouldn't actually be able to see that lone pair. So that's why we're going to see a difference in the molecular geometry in those cases. Okay. So when we look at ammonia, for instance, NH3, we're going to wind up with just the 3 single bonds going to each hydrogen, and then a lone pair on that nitrogen to fill its valence shell. So the structure is going to have 4 electron domains. Or I should say the central atom will have 4 electron domains, because we've got 3 bonded atoms and then a single lone pair on it. So when think about the way that they're going to spread out, if we go back for a second, the 4 domains are going to be tetrahedral, 109.5 degrees. But we're going to see that actually will change slightly with ammonia, because we do have one of those domains being a lone pair. But the best way for those 4 domains to spread out will just be that tetrahedral shape. So when we think about the electron geometry, for ammonia at least, it would be tetrahedral. But then, like I said, with the molecular geometry, when we do have lone pairs, that is going to be different. If we just had bonded atoms off the central atom, then the 2 are going to be the same. But when we have lone pairs, if you kind of just skip ahead to the end here, when we have lone pairs, when we actually think about the 3-dimensional shape, we're not going to be able to see those lone pairs anymore. So the molecular geometry is just showing us what we would actually kind of see if we could blow up that molecule to something we could visualize with our own eyes. So with the case of ammonia, we're not going to wind up with a trigonal planar, because this 4th electron domain where we have those have that lone pair is still going to affect the bonds here. So these electrons in the lone pair are still going to push those bonds down. And that's why we're still going to wind up with a slightly raised structure with the nitrogen in the middle, and then all of these hydrogens getting pushed down to the corners of this tetrahedral, because that lone pair coming off the top is still going to repel the electrons in these bonds. So again, with the electron geometry, we're simply just thinking about how many domains are on that central atom. But then if any of the domains are lone pairs, when we get the molecular geometry, it is going to be slightly different, because we're not actually going to be able to see those lone pairs. So if we look at just a couple, with CH4, methane, we're just going to have 4 bonded atoms. So that's why the electron geometry and the molecular geometry are going to be the same. They're both going to be tetrahedral. But then with ammonia, we've taken one of those bonded atoms. We, of course, switched the central atom from carbon and nitrogen. But then we took one of those terminal atoms and just changed it to a lone pair. So it's still tetrahedral in terms of the electron geometry, but with the molecular geometry, we would just have the trigonal planar, because now we're not going to be able to see that lone pair. And then the same thing still if we replace one more. So in the case of water, H2O, now we've got 2 sets of lone pairs and 2 bonded atoms. So we still have 4 electron domains. So in the electron geometry would still be tetrahedral. But now that we've replaced 2 of those bonded atoms with lone pairs, now we can only see 2 of those domains. So we can only see that bent shape. And then when we're looking at so if we just skip ahead for a second, we're going to see the differences between those when we've got the different number of bonded atoms and lone pairs. When we got 2 electron domains, what we're going to see is that it's always going to be linear, because the best way for 2 electron domains to spread out is just going to be 180 degrees. So something like carbon dioxide, for instance. And then with this, you'll notice that we're not going to have anything that just winds up being 2 atoms. So we could replace one of these bonded atoms with a lone pair. But in that case, we're only going to have 2 atoms. And the best way for two atoms, or the only way for two atoms to be connected, is just going to be a straight line. So that's why the molecular geometry, if we ever just have two atoms, is always going to be linear. Just because if we've only got those two, we can only just have them in that straight line. But now if we've got three electron domains, if all of them are bonded atoms, the best way to spread out is just going to be that trigonal planar shape. But now if we take one of those and replace it with a lone pair, what we're going to see is, again, just that bent shape. The bond angles will be slightly different than what we see with the bent shape in the next one. So if we replace two of them, we'll still wind up with a bent shape, but it is going to be a different bond angle in that case. But with this one, we've already kind of seen it, so I'll just skip ahead. But again, if we went one more further and just had one bonding domain, three sets of lone pairs, then we would still just have those two atoms. It would still just be a straight line there for the molecular geometry. And then when we look at the shapes here, the bond angles, in a tetrahedral, we're going to have 109.5 degrees, because that's going to be the angle at which all of these can spread out as much as possible. All four of these can be 109.5 degrees. But what we're going to see when we take one of those bonded atoms and replace it with a lone pair is that you can kind of think about the electron density in that spot is going to be greater. So what it's going to do is force those other bonds closer together. So in the case of ammonia, the lone pair here is actually going to force those bonds and hydrogen down a little bit more. So that's why we see the bond angles for the hydrogens get compressed slightly. So they go from 109.5 to 107. And then the same thing still, if we were, for water, for instance, replace another one of those bonded atoms with a lone pair, now we've got more of that electron density there. So it's essentially forcing those other bonds closer together, because these lone pairs you can kind of think about are going to take up more space almost in terms of the amount of electron density they're going to have. So it's going to force the other electrons in these bonds just to get pushed a little bit tighter. And that's why we see the bond angle start to decrease slightly as we start to add more and more lone pairs on that central atom. And then similarly, when we've got double or triple bonds, that's going to affect the bond angle as well. So again, in this case, we're going to have a higher density of electrons with the double bond. So what that's going to do is repel the other bonds more. So we'll see the bond angle involving that multiple bond is going to become greater. So if we think about this, if it was all equal, it would be 120. But because now that we've got more density on that double bond, we've got more electrons there, we've got a greater negative charge, it's going to repel the electrons in the other bonds more. So we're going to see those get pushed down a little. And that's why instead of 120 here, this bond gets pushed down a little, this bond gets pushed the other way a little. So instead of 120 for each of these, it increases slightly to 124, which then means the resulting angle between those two carbon-chlorine bonds has to get a little bit smaller there. So with these, if you can kind of just think about where we're adding more and more electrons, that's going to be where we actually see the bond angles increase. But because everything still has to be kind of spread out the same amount, the other angles are going to have to decrease accordingly. And then if we continue with the number of electron domains, so we've seen 2, 3, and 4. In this case, we've got a fifth one. So in this case, we're actually going to be exceeding the octet on that central atom. So something like PCl5, where we've clearly got 5 different bonded atoms, or even these other ones where we're going to have lone pairs involved. The electron domain, or the electron geometry, I should say, is going to be trigonal bipyramidal, because the best way for those domains to spread out will be that triangle in the middle, with each plane or each pole having the fourth and fifth electron domain. But as we start to replace those, what we're going to see is that the molecular geometry, just like the previous ones, is going to continue to change. And with this one, it's actually going to be important where the lone pairs go. Because with this one, we're going to see actually different bond angles. So around the central atoms, the equatorial ones, the ones making the triangle here, that bond angle is going to be 120 degrees. But it's only going to be a 90-degree angle between the equatorial and then the two polar ones, if you want to think about them as north and south pole. So when we actually go to add on a lone pair or a second lone pair or a third lone pair, what we're going to see with these is that they're always going to replace the equatorial ones, just because those are going to be more spread out. There's a greater angle there. It's 120 degrees, whereas these ones are just 90. So it's going to allow that electron, that lone pair, to be further away from everything else, basically. And that's why when we go from no lone pairs to a single one, we're going to see what's known as a seesaw shape. It'll be a little bit easier in the lab where we're actually working with the model kits. But with this one, what we're going to see is that you can essentially just kind of tip it back and forth, just like a seesaw, because we're going to have the uneven, sort of the uneven bent shape with the equatorial ones now that we've replaced one of them with a lone pair. And then as we go one further, now we're going to wind up with a T shape because we've gotten rid of two of those equatorial ones. So now we're just going to have a 90-degree angle in both directions coming off the lone terminal atom in the middle. And then again with the three lone pairs, now we're just going to wind up with a linear shape because we've replaced all of the equatorial atoms with the lone pairs. And then we've just got the ones on the top and the bottom that are just going to be in a straight line with that central one. And if we went one step further, again, we just have two atoms in that case. And just like always, that would give us a linear shape as well. So again, with them, this one in particular, we've got the equatorial. And then we're going to refer to them as the axial ones, the ones you can kind of think about the North and the South Pole. And like I was saying, since the equatorial ones are spread out by 120 degrees, that's why when we add the lone pairs, they're going to replace the equatorial atoms rather than the axial ones, just because that bond angle is going to be larger there with the 120 degrees. And then just like with the previous ones, as we do add those lone pairs, we're again going to see the bond angles are going to change. So with a full set of 5 bonded atoms, 0 lone pairs, we've got 120 degrees around the middle, 90 degrees to the axial. But now that we've added one of the lone pairs, so sulfur tetrafluoride, now that we've replaced one of those bonded atoms with a lone pair, what we're going to see in the middle is that this bond angle is going to go from 120 to 116 because that lone pair coming off the other side is going to squeeze it a little bit essentially. And then we're going to see kind of the same thing with the top one. If we're looking at the bond angle in this direction, instead of 180, now it's going to be a little bit larger because each of these fluorines, you can kind of think about it, if he's got the lone pair coming off the left here, each of these fluorines in the axial position are going to get pushed to the right slightly. So that's why if we're measuring the bond angle up in this direction, we're then going to see it get increased a little bit because each of these fluorines got pushed over to the right a little bit. And then if we continue with this, we can see the octahedral. So now we've got 6 electron domains. And with it, all of these atoms are going to be spread out by 90 degrees. So in this case, we could actually kind of take the molecule, and if it was the same atom on the outside, we could essentially flip it 90 degrees, and it would be exactly the same. We would just be switching the axial electron domains with 2 of the equatorial, but it would still basically be the exact same thing, assuming all of those terminal atoms are the same. But then when we replace one of the terminal atoms with a lone pair, in this case, what we're going to see is we're going to consider it the axial one, and we'll see why when we get to a second lone pair. But in this case, it could basically replace any of the electron domains, because again, they're all going to be separated by 90 degrees. But when we do this, if we consider the bottom one being the one that gets replaced with a lone pair, now we're going to say it's a square pyramidal shape because we've still got the square around that equator, and we just have a single axial atom. So when we're actually looking at the molecule, we wouldn't be able to see this lone pair at the bottom. So we would just kind of see a square with just one atom coming off the top there. And then the reason we're going to consider the axial ones as the ones that get replaced is going to be because now if we've got a second one, the lone pair is going to go in the opposite spot. So we can just kind of make it easy visually and replace both of the axial positions, rather than it gets a little bit harder to see if we do some of the equatorial ones. But now we don't have anything on the top or the bottom. We've just got that square in the middle. And that's why we're going to refer to this when we've got 4 bonded atoms, 2 lone pairs on that central atom. We're going to refer to this just as the square planar shape, because that's exactly what we've got. We've just got a square, and it's going to lay exactly flat. So if we did have this molecule, we could lay A and all 4 of the B atoms on the outside. We could lay them just on the same flat surface because they're going to be in the exact same plane. And then we could, in some cases, I suppose, have examples where we've got even more. But in that case, we would just start to remove from the equatorial positions. So we would have a T shape if we removed a third one, and we would just wind up with a linear shape if we removed a fourth one. So what we can do is look at a few examples. And with this, I'm going to kind of just go ahead with the first one at least, because we've seen ozone before. So we're going to have oxygen. And then if we think about the Lewis structure, we'll have 1 double bond, 1 single bond. And then we'll fill in the lone pairs there. In reality, remember, we'll have resonance here because we could have the double bond in either direction. So we really kind of got a bond and a half. But either way, we'll have 2 bonded atoms. We'll have 1 set of lone pairs. So we'll have 3 electron domains. So when we think about the electron geometry, we're going to have trigonal planar, because we're going to have 3 domains. So the best way for them to spread out is going to be about 120 degrees. But we're going to see the angle is going to be at the reason I said about 120 degrees is because we do have the lone pair here, which is actually going to force the angle between these 2 bonds to be slightly less than 120 degrees. So in this case, the molecular geometry would just be bent, because we've got those 3 domains, but one of them is going to be a lone pair there. And then with the next one, tin chloride, or tin 3 chloride, I should say. What we're going to see is this one will actually work out. We've got 4 electrons coming from tin. We're going to get 21 from the 3 chlorine. And then we're going to get a 26 just from that negative charge. So we'll have 26 electrons in total to work with. So when we look at the central atom here, we're going to put the chlorine, or the tin rather, excuse me, SN in the center, surrounded by the 3 chlorine. And then we'll add the lone pairs to fill those in. So we've got 6, 12, 18, 20, 22, 24. So we can go in and add the 25th and 26th there. And then we'll put brackets around it. So we're able to fill the lone pairs, everything, but we put brackets around it, put the charge there to show that it's going to be a polyatomic ion. But now when we look at it, we've got 4 electron domains. So we're going to have tetrahedral for the electron geometry. But since we replace one of those bonded atoms with a lone pair, we're not going to have the same for the molecular geometry. In this case, what we're going to see is trigonal pyramidal. And the reason it's trigonal pyramidal rather than trigonal planar is because of that lone pair on the tin in the center. Since we've got that 4th electron domain, these 3 are all going to get pushed down. And that's why we'll have the tin slightly raised up. And that's why we don't have planar, we've got pyramidal, because the tin's going to be slightly higher than the chlorine, because this lone pair on tin is going to force those bonds to get pushed down a little bit. All right. And if we continue, whoops, with SF4, sulfur is going to give us, oops, I want to do draw. Sulfur is going to give us 6. Each fluorine is going to give us 7, so we'll wind up with 28. So we'll wind up with 34 in total. So we'll put sulfur in the middle. Okay. And then for this one, just because the dots don't really come out very well, I'm not going to draw in the valence shell for fluorine, but each of them will have 6 more electrons around it just to give it the 8 it needs to fill its valence shell. So we'll have 6, 12, 18, 24, 26, 28, 30, 32. So what we're going to do is just add on the 33rd and the 34th electron on that sulfur. And what that's going to do then is give us a 5th electron domain. So our electron geometry is going to be trigonal bipyramidal. But because we've replaced one of those lone pairs, or one of those bonded atoms with a lone pair, what we're going to see is that the molecular geometry is going to wind up being seesaw. Because remember, with the trigonal bipyramidal, when we've got 5 electron domains, we've got the 3 around the center, giving us a triangle, and then we've got the 4th and the 5th just in the axial position on the top and the bottom. But when we go to add a lone pair, we're going to replace the central, we're going to replace the equatorial domains first with the lone pair, and that's why we're going to see a seesaw shape in reality. And then with IF5, we can do the same thing. In this case, we've got 6 halogens, so we're going to wind up with 42 electrons. We'll have the terminal fluorine. And again, I'm not going to draw in the lone pairs, but that's going to use 30 electrons just to give the lone pairs on each of these fluorine, give them the 6 they need to fill the valence shell. So 6 times the 5 fluorine gives us 30. And then we've got 10 more in these bonds. Oops, and that was not. So now when we look at it, we've got the 41st and 42nd just in the lone pair on iodine. So we've got 5 bonded atoms, 1 lone pair. So we've got 6 electron domains. That's going to give us the octahedral shape. Oops. Oops. Okay, so we lost it. All right, so we lost it all. But with the IF5, we saw that it had the 5 bonded atoms, the 1 lone pair on it. So what we're going to see is the 6 electron domains. We're going to have the octahedral shape where we've got the square in the middle or around the equator, and then the 2 axial ones. What we're going to see is that we replace one of the axial positions first with the lone pair. So the molecular geometry for IF5 would just be square planar, because we're going to see the 4 fluorine around the equator, and then just see the 5th one coming off the top there. And if we continue, we can look at a couple more. And if you want to practice with these, you can pause it and then just give yourself a little bit of time to work through it. But for this first one, we're going to have 28 electrons. And what we're going to see ultimately is that we'll have the 3 fluorine, and then we're going to wind up with, whoops, 2 sets of lone pairs on that chlorine. So we're going to again have 5 electron domains like one of the previous ones. But in this case, we've replaced 2 of those lone pairs. So again, with 5 electron domains, we're thinking about trigonal bipyramidal. We're going to have 3 around the equator, 1 on the top and the bottom. But with the trigonal bipyramidal, we're going to replace the equatorial position first. So we're going to replace 2 of the ones around the sort of the middle in that triangle with the lone pairs. So in this case, with CLF3, we're going to see that we're going to have a T-shaped in this case. And then with the final one, ICL4, we're going to have 5 halogens. So we should have 35 electrons. But since we've got a negative charge, we're going to have the 36. And then with it, we're going to have 4 bonded atoms for the 4 chlorine. And again, the reason I'm just not showing the lone pair electrons on the terminal atoms is just because it's hard to do with the mouse and have it be sort of legible. But then also the lone pairs on those terminal atoms aren't going to influence the geometry coming off the central one. So they're not going to influence the actual shape we see here. But with the polyatomic ion here, we've got 36 electrons. If we have 6 in the lone pairs around each of these chlorine, we're going to have 6, 12, 18, 24, 26, 28, 30, 32. So what we're going to see is 2 sets of lone pairs on this. And then with it, I'll also show in class, it's just going to be a little harder to do with the mouse here. But in class, what I'll show is how we can actually add bold dashes or bold wedges or dashed wedges to this to kind of show 3-dimensional shape a little bit better, show which of these chlorine bonds is coming out of the plane of the screen, which ones are going into the plane of the screen. But with this one, since we've got 6 electron domains, we're going to have an octahedral electron geometry. But now that we've replaced 2 of those domains with lone pairs, what we're going to see is the axial, so the top and the bottom, are going to be what gets replaced with the lone pairs. And the 4 bonded atoms are now just going to give us the square around the middle there. So in this case, we're going to have square planar for ICL4 versus T-shaped for CLF3. And then with it, the previous ones, what we've been looking at was just the sort of the simpler examples where we've just got one central atom and then we've got terminal atoms on the outside. But we can use this geometry and apply it to larger molecules as well. It's just in the case of something like this, we would want to consider all of the atoms in the middle here. So the 2 carbons and then this this 1 oxygen that has the 2 single bonds going to it. We would want to kind of consider all of these to sort of be central atoms. And what we're going to see is we're going to have a geometry coming off of each of them. So with the first carbon, we've got 4 bonded atoms, no lone pairs. So we're going to see a tetrahedral geometry there. These are all going to spread out by 109 degrees. So we would have the tetrahedral shape for this portion. With the second carbon here, now we've just got 3 bonded atoms because one of those has a double bond. Again, still just counts as 1 electron domain because all of the electrons in this double bond are essentially grouped together. So what we're going to see is a trigonal planar geometry here. So we're going to have 120 degrees between these different bonds. Again, it'll be a little different because we're actually going to wind up with slightly larger angles between the carbon-carbon oxygen than we will for carbon-carbon hydrogen or something like that. Just because we'll have more density here, which forces these bonds to get pushed down a little bit. But it'll be roughly 120 degrees here because we've got the 3 electron domains, and that's going to be the most efficient way for those to spread out. And then when we look at the geometry around this oxygen, now it's got 2 bonded atoms, but it's got 2 lone pairs. So the geometry for the electron is going to be tetrahedral still because it's got those 4 domains. But when we look at the shape of it, we would see kind of a bent structure for this portion of it because we've got the two domains being lone pairs there. So when we're looking at larger molecules and we want to consider the geometry, we need to look at each of the central atoms. So anything in the middle, we need to look at the geometry of that, see how many domains we have coming off of that atom, see what are lone pairs, what are bonded atoms, and that's going to affect the shape of the molecule as a whole. So when we actually do look at, what would this be? Ethanoic acid. In this case, we're going to have an organic acid. This is the functional group there, carbon double bonded to oxygen, and the OH coming off of it as well. When we actually look at the structure of it, like we said, we're going to have a tetrahedral shape around this carbon. That's what we can see with the different bonds here. We're going to have a roughly trigonal planar shape on this one because we've got 3 electron domains. And then with the oxygen here, we don't see them because we've got the 2 lone pairs. But that's why we've got a bend shape when we look at the carbon-oxygen-hydrogen bond here. If we didn't have any lone pairs, we would just have the hydrogen coming off in the same direction as the carbon-oxygen. But since we do have those lone pairs there, that's why we see this hydrogen bond get forced down, because we've got the electron density on top as well. And then the reason this is also going to be important is when we think about larger molecules, now we're going to have different electron density throughout. We're going to have different elements mixed in. So some are going to be more or less electronegative. We're typically going to see with these larger molecules, there's going to be one portion of that molecule that's going to be more reactive than the rest of it. And having an understanding of the geometry helps explain why that might be. Because in some cases, having a whole bunch of hydrogens or having something that's actually sort of covering an atom can reduce its reactivity. Whereas if we have something that's really well exposed, like the oxygen, now that may be more reactive. And then when we're looking at the molecule as a whole, we can also consider the polarity of it. So if we look at something like carbon dioxide, we talked about the bond dipole in the previous chapter. So we've got difference in electronegativity. When they're sharing those electrons, they're just not going to share evenly. So in the case of, oxygen is going to be more electronegative than carbon. So with the dipole moment, the arrow is showing where the negative charge is going to be. So each of these carbon-oxygen double bonds, we would see the oxygen would be slightly negative, carbon would be slightly positive, because the oxygen is going to be more electronegative. It's going to be better at pulling those electrons closer. But now when we look at the molecule as a whole, we need to consider the bonds we have, but we also need to consider the symmetry of the molecule as a whole, because with carbon dioxide, we're going to see that this is going to be a non-polar molecule, because each of these bond dipoles is essentially going to cancel each other out. So with the arrow here, what this really is a vector. So it's showing the magnitude of that bond dipole, but it's also showing the direction of it. And since each of these are the same magnitude, but they're pointing in opposite directions, they're going to cancel out. And that's why we've got an overall dipole moment of 0. And that's going to be the case anytime we've got symmetry. So anytime we don't have lone pairs on the central atom, and we've got the same thing on the outside, each of these bonds is going to basically cancel each other out. And that's why we're going to see things like carbon dioxide are going to be non-polar, even though we've got 2 bonds that we could consider polar. And that's why when we look at something like water, we can see that this is going to be highly polar, because now when we look at the bond dipole for either of these bonds, hydrogen is going to be positive, oxygen is going to be negative. So that's why we can see the arrow going from hydrogen to oxygen, again, pointed towards the negative. But in this case, each of these hydrogens are pointed down, because we've also got the lone pairs on this oxygen that push these bonds downwards. So when we look at the sum of this bond dipole, of these bond dipoles, they kind of cancel each other out in terms of left to right, because this one's moving left just as much as this one's moving right. But both of them are pointed upwards. And that's why when we look at the sum here, the overall dipole moment, we don't see a 0. Now we've got some dipole left. And that's why we're going to see a highly polar molecule with water, because the oxygen is going to be very negative. The hydrogens are going to be positive. And that's why we see a difference in the electron density here. So whereas carbon dioxide is symmetrical, basically balances out. That's why we've got the same thing on the left versus the right. With water, we don't see that. and that's why we've got a difference in the electron distribution of the electron density here. So if we look at the few examples we have here, again, the simplest way to kind of check is to see if we have lone pairs on that central atom, and to see if the atoms on the outside are different. Because in the case of something like CH4, or CH3Cl, excuse me, we've got no lone pairs on the bonded atom. So each of these domains are going to be able to spread out as much as possible. And if all four of them were hydrogens, each of these bonds would essentially balance out, kind of like we have here with CCl4, carbon tetrachloride. All of these are chlorines. We have no lone pairs on that carbon. So each of these would be able to spread out as much as possible. And then each of these bonds would actually cancel each other out. We'd wind up with an overall dipole moment of 0. That's why we'd consider this to be nonpolar, even though each of these bonds is polar. But now with something like this one, we don't have the same thing on the outside. So even though we've got 4 electron domains that are all bonded atoms, the dipole moment of this bond isn't going to be canceled out by the dipole moment of the other 3. And that's why we see something like this is going to be polar. Whereas ammonia, we've already talked about, we do have the lone pair coming off of this nitrogen. So because we have that lone pair there, it forces these bonds down. And because of that, we see an overall dipole moment getting pointed up towards that nitrogen, just because they're not going to cancel each other out with these bonds. Whereas BF3, this is going to be an example where we've got an electron deficient central atom, so it's not going to have any lone pairs, even though we've just got 3 single bonds to it. But because we don't have any lone pairs there, these bonds can spread out just as much as they want, 120 degrees. And since all 3 of these atoms are the same, the dipole moment is going to be the same. So we're going to see that it's actually going to cancel each other out. So if we look at this one, for instance, may not be totally evident why it's going to cancel out, but this is going to fit or lay flat on a desk. So there's going to be nothing about going up and down. So if we just kind of think about looking at it from the bird's eye view, each of these is going to cancel each other out in terms of going left to right as we look at it here. But then each of these combined is going to balance out this one in terms of going up and down. And then similar with this one still, but in this case, we do have kind of an up and down, left and right in every direction, since we do have a 3-dimensional structure rather than a planar one. And then with something like HCl, we just have that single bond. So if we've just got one bond and it's polar, then the molecule as a whole is going to have to be polar too. So again, with these ones, it's not always going to be the case, because if we have something that's octahedral shape or octahedral electron geometry, but 2 of the lone pairs are 2 of those domains, what we're going to see is that the excuse me, the square planar one could still be nonpolar. But for the most part, if you do have lone pairs in that central atom, or if you've got different atoms on the outside, typically that's a good indicator that it's going to be polar. But there is the case with the square planar, where we've got 4 bonded atoms, 2 lone pairs on the central one, where it could still wind up being nonpolar there. So if we look at a couple examples, this will be the last little piece here. So if you want to practice with this one, with these ones, we just want to kind of pause it and give yourself a little chance. But with BRCL, doesn't even matter what the lone pairs are. Ultimately, we'll just have 3 sets of lone pairs on each of these. But that's not important, because we've got 2 atoms, 2 different atoms bonded together, and that's all we have. So we're going to see some bond dipole moment here. So this would be polar. So I'll do P. With SO2, we'll wind up with 18 electrons. So that structure should be 6, 12, 14, 16. So we'll have one double bond. All right. So we'll wind up with this structure here. Actually, we'll wind up with that, so we can minimize the formal charge. So we'll wind up with two double bonds. So similar to carbon dioxide, but in this case, we've also got a lone pair there. So that's going to push these bonds down. And since we've got that lone pair there, we're going to see that this is going to be polar. And then with the final one, I'm not even going to go through that structure, because what we're going to see is we'll have sulfur with no lone pairs and just 6 bonded fluorines to it. But because all of those fluorines are the same, because there's no lone pairs on the central atom, this molecule is going to be symmetrical. So each of those sulfur fluorine bonds are essentially going to cancel each other out. And that's why we're going to see the molecule as a whole is going to be nonpolar, even though each of those bonds would be polar. But that will be where we wrap this one up. And then we will continue with the rest of chapter 9 in the next video.